Last class in topic 1.4, we introduced the idea of polynomial equations. We talked about the extrema, we talked about points of inflection, but polynomials have a ton more vocabulary and 10 more things we can talk about in regards to them. So today is kind of like a little bit of an overview of polynomials. Again, you learned about polynomials in Algebra 2, so some of this is going to sound familiar. I might be changing your notation or maybe tuning up some of the things you learned last year, but for the most part, we should know these things or at least be familiar. First things first, when we're talking about a zero of a polynomial function, we are talking about the places where the graph crosses the x-axis. It is when the function p of a is equal to 0, which is called a zero or a root or an x-intercept or a solution for the polynomial. You'll see all of those, but we use the word zero the most. It is a zero of the polynomial function. If a, which is the number that a zero would be equal to, so if x is equal to a, and it's a zero of p, then we automatically know that the linear factor that creates that part of the polynomial is, in parentheses, x minus a. So we're going to have these factored form polynomials, x plus or minus some number, x plus or minus some number, but whatever that number is, that's in the parentheses, that is coming from the place where the graph crosses the x-axis. So if we look at this function that I have graphed there for you, we have y equal to negative 0.01 x plus 4 times x plus 1 cubed times x minus 3 squared. It's graphed over there. Let's notice some behavior around the zeros of the functions. Well, first of all, if we look at the zeros, we have 3 places where this graph crosses or touches the x-axis. Do you agree? We have 3 distinct zeros. 3 distinct places where this graph is going to cross the x-axis. 3 distinct real zeros. Let's list them. What is the first distinct real zero that you see? Negative 4. At negative 4, what is happening with the graph? It's increasing. Okay, cool. Yeah, great. I was actually looking for it's passing through. So the function is passing through the x-axis at that point. You're right. It is increasing. Love that. Let's keep thinking in that way. But at that 0, our graph is crossing through the x-axis. Seems like, yeah, duh. Okay, I'll tell you why that's important in a second. What's the next 0 that you see? X equal to negative 1. What's happening there? Passes through. Right? It goes boop, passes through. What is happening at, or where is the next 0? 3. What's happening there? It just touches it. We're going to call that a bounce. That's not super mathematical vocabulary. I will give you the mathematical word in a second, but it like bounces off, yeah? So we have 2 things that can happen at each of our zeros. We can either pass through or we can bounce off. Those are the things that we can notice that zeros will do in a function. Now, how do you determine whether it will bounce or pass through? I'm so glad you asked. That has everything to do with what's called the multiplicity of the zeros. Multiplicity of the zeros. If a linear factor, x minus a, is repeated n times, then the corresponding zero has a multiplicity of n, meaning it will look like this. You'll have some factor for your polynomial, and it will be raised to some power. This is the multiplicity. Most factors that you would have seen up to now probably didn't have a power showing. That's because they're multiplicity 1, and we don't need to show exponents of 1 because that's annoying. We don't have to do that. But a multiplicity of the 0 is the degree, you can think about it, the degree of its factor. That looks like a degree for each parentheses. And the multiplicity controls what happens at that 0. If you have an odd multiplicity, at odd multiplicity, the graph of the function passes through, I'll actually spell the word through out correctly, passes through the x-axis at this 0. For an even multiplicity, so if you have a squared factor or you have a factor to the 4th power, that is when the graph of the function is going to bounce off. But we're going to call it, the graph of the function is tangent to the x-axis. You can think of that as your bounce. Maybe put bounce in parentheses. Being tangent to something means that you touch it once and you bounce away. That's exactly what's happening. That's our bounce, called being tangent to the x-axis. So let's look back up at what we did just a second ago for that function. Can we think about the kind of multiplicities we would have? For the 0 that passes through, we should have some sort of odd multiplicity. Same here, odd multiplicity. Same here. Well, not same here, but here, since it bounces or is tangent to the x-axis, we should have some sort of even multiplicity. Now, does this make sense for the function that we have? It 100% does. What's the multiplicity of this factor? The one that I've highlighted. 1. That is the one that creates this 0. X plus 4 means that x is equal to negative 4, opposite sign. That is an odd multiplicity. It's a multiplicity of 1. What's the multiplicity of this guy? 3. So x equal to negative 1, which comes from this factor, x plus 1, x equal negative 1, right? Passes through because the multiplicity is odd. That's an odd number. But if you notice, at this one, what kind of multiplicity do I have? Even. So that is why we are tangent to the x-axis at that point. We're going to bounce off because we have an even multiplicity. So you can tell what's going to happen on a graph just from seeing the equation in factored form. You don't even need a graph, which is great. So we're not going to graph stuff today, but we're going to tell a lot of things about polynomials. So for each of these polynomials down here, we're going to determine first the degree of the entire polynomial. We're going to find all of the real zeros and state the multiplicity for each 0. Great. I'm going to tell you right now that this first one has a degree of 6. How am I getting that answer? With doing no work. Like, I didn't do extra work and just be like, I can multiply fast. I know right away that this has a degree of 6. How do you think that's possible?
Oh, because it's
Yeah. So not multiplying the exponents. I'm counting the number of x's that would be involved if I were to multiply it out. How many x's are here?
3.
How many x's are in this guy?
1.
How many x's are in this guy?
2.
2. So 3 plus 1 plus 2 is what? As finding the degree. If we were to multiply all of this out, we'd end up with a degree 6 polynomial where you could see it. But if you count the number of x's, there are 3 x's in this factor, there is 1 x in this factor, and there are 2 x's in this factor. That's 6 total. Yes? Now, I want to take a few shortcuts here. I'm going to tell you right now that the zeros of this function are at 0, are at negative 1, and are at 4. How do I know that? Yeah, so in the parentheses ones, those are really simple. Okay, so I see x plus 1. Ooh, iPad just turned off. We see x plus 1, so that means a factor, or a 0 is x minus 1. This factor says x minus 4, so what does that mean the 0 is? Positive 4. Now, where did this 0 come from? Yeah, this one right here, what number is in the parentheses with x? Air quotes, in the parentheses. There's no number in the parentheses, right? 0. If you were to set each factor equal to 0 and solve, which is analytically what you would do here, you would solve negative 2x cubed equal to 0, and x would have to be 0. So I have the 3 distinct real zeros, but there is repetition in these zeros. So what we're going to do to state the multiplicity is right behind it, you're going to put the word mult for multiplicity, and you're going to tell me how many times that 0 repeats. So for x equal to 0, what is the multiplicity of that factor? Number-wise. 3. It is odd. It would pass through at this point. These are all things we know. What is the multiplicity of the factor x equal to negative 1? 1. So we would say multiplicity 1. What is the multiplicity of the factor x minus 4? 2. So at this point, here's some things I would know about this polynomial. I would know it's degree 6. It will have 6 zeros. I can see that it will cross the x-axis at 0. It will cross the x-axis at negative 1, and it will be tangent to the x-axis at 4. We'd have a lot of hints on how to graph this function just from the multiplicity alone. Make sense? The only way I can make this harder is if it looks like question B. Why is this one different than A? It's not factored, so we're going to have to factor it. But before we do, we can totally answer the degree of this polynomial. What's the degree? Okay, thank you for saying that because I'm realizing that now, yes, that would be very confusing. You're multiplying leading terms here. So this one and this one would add up to how many? 4. I know that there's an x here, so you're right. Thank you for listening to me, but that was wrong. This x is not going to change the degree of the polynomial, just the largest x in each factor. So if we look back on this one, we only technically paid attention to the largest degree in this factor, the largest degree in this factor, and the largest degree in this factor. Okay? So for this one, this is going to be degree 4. We know we should have 4 different zeros, especially when we start counting multiplicities. But let's factor. Do we remember how to factor? Okay, this first one is the difference of 2 squares. What does the first factor multiply out to? Oh, here's a hint. 4 can be written as 2 squared, yeah? X minus 2 times x plus 2. Yeah, difference of 2 squares. It's subtracting 2 terms that are perfect squares. We take the things that are squared and do the first minus the second, the first plus the second. That's the difference of 2 squares. Now, if we factor the second one, at this point, I don't know what method you used last year to factor. I like the guess and check method. Do y'all know what that is? Kind of. Okay, thank you for your honesty. The guess and check method is doing an X puzzle in your head. Do we know the X puzzle method? Yes. Great, we're going to do it in our head. What we do here is we set up 2 parentheses with an X in front. We ask ourselves, what are the numbers that multiply to 8? 4, 2, and what else? Oh, 8 and 1. It's going to have to be one of those pairs of numbers. In the guess and check method, you just try. So let's try 1 and 8. I like going in number order. I try this, being ready to erase it if it's wrong. We check the outsides and the insides. If you were to multiply that, it would be 8x and 1x. Can you make the number 6, negative 6, from 8 and 1? No. Okay, so that was wrong. We erase. Oop, I erased too much. We try again. You just have to erase the numbers. My eraser was too big. So we try, what did y'all say, 2 and 4? Okay, this would be 4, this would be 2. Is there a way to make negative 6 out of 4 and 2? If they're both negative, right? Okay, great. So we just totally did factoring in our head. That is exactly what you did with an X puzzle all last year, if that's what you used. We're just doing it now in our head, and it should go a lot faster. Okay, fabulous. So I have this whole thing written out, and I'm going to rewrite it one more time before I start answering this question. And I'm going to rewrite it like this. Why did I do that? There are 2 factors that say x minus 2. Let's write them together so we can see very easily the multiplicity of that factor. The zeros for this function are x equal to 2, are x equal to negative 2, and are x equal to 4. Do we see where I'm getting those numbers from? What is the multiplicity of the 0 x equal to 2? What is the multiplicity of x equal to negative 2? And what is the multiplicity of x equal to 4? If you're like, whoa, where are y'all getting these numbers from? Thank you for asking. Here. The zeros associated with each linear factor have a power. Some of them don't show because we don't write exponents of 1 because it's annoying. Make sense? Now, one thing I want to quick check for ourselves every time we do one of these, when we're finding the multiplicities, they should add up to the degree. So even though I only found 3 distinct zeros, if you count their multiplicities, that's 1, 2, 3, 4, degree 4. Yeah? And here we had 1, 2, 3, 4, 5, 6, degree 6. So it should all total up. Yes?
What did negative 2 be 2?
Yes. Okay, so this, are you saying here because this says negative 2? If I were to show my work on this, when we're actually solving these polynomials, what you do is you set each factor equal to 0 and solve. How do you solve for x here? Add 2 to both sides, right? So the shortcut is it changes sign. So if you see x minus 2 in a factor, x equal to 2 is what you take out. Because the linear factor is always x minus some number. So if it's a positive, it's minus a minus. And those, so far, we've talked about the real zeros of a polynomial. And we all know that sometimes polynomials don't have real zeros. Because if you look here, how many times does this graph cross this x-axis? 0 times, which means we don't have any real solutions to it. We're going to have, what kind of solutions? Do we remember? Imaginary solutions. Amazing. So sometimes complex numbers are involved. Some polynomials have roots that contain an imaginary number. This means you will not see them on a graph, which is why we need to know how to do this analytically. So for example, this graph is actually x squared plus 1. To find the zeros of x squared plus 1, since we cannot factor it, and since it cannot be seen on a graph, we're going to have to do this by hand. So if I were solving x squared plus 1 equal to 0, the first thing I would do would be subtract 1 to both sides. And then I square root. Anytime you actively take the square root of something, what do you have to put in front of it? Plus or minus. So I'm doing plus or minus the square root of -1. What is the square root of -1? It is your imaginary term or your imaginary number. That's I. As a handwriting note, I highly recommend you making your eyes a little bit curvy. Otherwise, you're going to think that it's a 1. Just from teaching a long time. Okay, curve your eyes a little bit. That way you know that they're the imaginary number, not just like a random like stray marking on your page. Okay? Yeah, I recommend that. Now, if you notice, when we did this, we took square root of something, so we put plus or minus, which means we have a pair of solutions here. Anytime you have an imaginary root, all imaginary roots come in pairs for that reason. Because we have to take the square root of something, we put plus or minus. They will always come in pairs. In fact, these pairs, if a plus bi is a root of f of x, then so is a minus bi. We just changed the sign of the imaginary part. The a could be a number, the b could be a number. These are called conjugate pairs or complex conjugates. They will always come in pairs. So if you see one, you have to know the other one is there. So let's just make sure we understand the concept of complex conjugates. We're going to just determine the conjugate of the following numbers. If I say that one of the roots is 4i, what's the other root? -4i. You have to know that. They go together all the time. If I say one of the roots is -i, what's the other one? Amazing. What if it looks like a complex number like this? If 2 minus 3i is one of the roots, what's the other one? 2 plus 3i. Yeah, you only change the sign of the imaginary part of this complex number. What if I say one of the roots is -4 plus 2i? Minus 2i. So the moment I tell you one of the imaginary roots, you know the other one exists. They come in pairs always. So let's put this all together. Some things that we might need to tell me about zeros, complex or not, our function has everything to do with the fundamental theorem of algebra. Fundamental theorem of algebra sounds really crazy because it's like got big words in the title, right? And it's a theorem. But it's really simple. A polynomial of degree n has exactly n complex zeros, meaning real or imaginary, especially when counting multiplicities. We kind of talked about this at the top. If the multiplicities add up to the degree, you're done. But you also now have to be careful because we know that there might be imaginary terms. So example 3 says, the graph of the polynomial function is shown in the figure on the right. It is known that x equal to I square root 3 is one of the zeros of f. If f has degree n, what is the least possible value of n? That's a lot of information. Let's just take a look at the graph itself. How many zeros do you see on the graph? You fell for my trick. You see 2 distinct zeros. But what's happening at -1? It's bouncing. So is there going to just be 1 there? No, it's going to be some sort of repeated root. There are 2 distinct zeros, but one of them is going to bounce or be tangent to the x-axis, which means we know that that's got an even multiplicity. So if we list out the zeros we can see, again, we saw that x is going to be equal to -1 with a multiplicity of probably 2, some sort of even number. We'll pick the smallest even number. We see that we have a 0 at x equal to 3. What's the multiplicity there? 1. then the problem itself says that we have a 0 at I square root 3. Your spidey senses should be going off. Because what is the other place where this has an imaginary 0? Negative I root 3. We know they go together, so we have to remember to include it, even if the problem only tells you one of the things. So if we have all of these, we have all the multiplicities listed. What is the least possible value for the degree of this function? I think I heard somebody say it. It's 5. Where'd the 5 come from? Adding up all the multiplicities. There are 4 distinct complex zeros, 2 real, 2 imaginary, but one of the real ones repeats. So that's 5 zeros. So the least possible degree of this function is 5. Does that make sense? This is a moment the students mistake. We accidentally forget this one, so don't forget your complex conjugate. We also forget that a bounce is happening here, so that's going to be some sort of even multiplicity. We assume 2 when in this kind of question. All right, we'll leave zeros for a second. We're going to talk about solving polynomials inequalities. First off, with a graph. This one's fun. It's coloring. Yay. If f of x is greater than 0, that means that the outputs are above the x-axis. If f of x is less than 0, that means that the graph of f of x is below the x-axis. So greater above, less below. Remember, f of x means outputs. So are the outputs above 0 or outputs below 0? So let's just color code for a second. Now we're not color coding concavity. We're not color coding increasing and decreasing. We're just color coding if it's above or below. So if I'm doing this, I'm going to make green be above because to me that means positive. I'm going to make pink be below because to me that looks like negative. And I'm also going to highlight the exact places where this graph is crossing or bouncing off the x-axis, because all of those pieces of information are going to be important for answering these questions. I've actually answered all of the questions here to kind of speed up our note-taking process since today is kind of long, but let's highlight these questions as well. Part A says, where does f of x equal 0? Well, f of x is going to equal to 0 at the zeros of this function. So you see how those numbers, -3, -1, and 3, are the places we've highlighted blue. Those are the zeros. That's where f of x is 0, is equal to 0. The next question asks, where is f of x greater than 0? So I have the open interval from -3 to -1 and from 3 to infinity. Do you see how I'm answering this question? These are the two intervals between those x values where the graph is green, where the function is above 0. But then the question changes. Part C says, where is f of x greater than or equal to 0? I need to include in my answer all of the places that are both green and blue, where it is above and equal to the x-axis. So what changed in my answer here? The brackets. What do brackets mean when we're talking about inequalities? Closed. We're actually including that number. So here I'm saying starting like infinitesimally after -3, we are above the x-axis. But here I'm saying at -3, we can include that number. We're exactly equal to the x-axis at this point, so we change it to the bracket. Do you see the difference? Now, one thing I want you to notice is, should you ever put a bracket next to infinity? No. Okay, great. You actually can't touch infinity because it's a concept, not a number. So we're going to always put a parentheses next to that one. F of x less than 0 is the next question. That's where it's below the x-axis. That's all my red stuff. So again, we're back to only parentheses because we are not including the places where we actually touch the x-axis. But when the question switches to be less than or equal to, we include brackets again, because now we can actually include those zeros in my answer. We can include the zeros in my answer. Cool? Okay, but what if we don't have a graph? And you're not on a calculator portion of the test. So we can't graph this thing to see where it's above or below. Here's how we're going to do this. I've got the steps written there. It says first, solve the function directly equal to 0, even if the inequality is one of the other symbols. We're going to do what's called creating a sign chart with the solutions that we found, with the zeros of the function. And we're going to test values in each interval to see if those outputs are either above or below the x-axis. If numbers are positive in that interval, that means all of the numbers in that interval are above the x-axis. Or if they're below it, we're going to get a negative number. So to show you what I want, I've already worked one example out on your notes. It says in example 4, to solve this polynomial x minus 3, x plus 1, x plus 4, all greater than or equal to 0. I find it helpful when I'm doing these to color code, so we're doing greater than or equal to 0, so we remember what our end goal is. We take the polynomial, we set it equal to 0. We discussed earlier how quickly we can go from factors to 0. So x minus 3 means this answer is 3. X plus 1 means this solution is -1. X plus 4, x is equal to -4. We still follow that part, right? So what I've done is I've made a random number line. I didn't even space the numbers out correctly because I don't really care. I just want to see the numbers on a number line. And I've put closed circles on this number line for these numbers. Why do you think I put a closed circle? Yeah, because I'm doing an or equal to, right? So I want to know, including these points, a closed circle as opposed to an open, we know that those points are going to be included because at least there it's equal to 0. Now, in this next part, these are 4 intervals. I have created an interval here from -infinity to -4, an interval between -4 and -1, an interval between -1 and 3, and an interval from 3 to infinity. Yes? What is a number that is less than -4? We pick an easy one, a -10, right? It's significantly less than -4, so it's like here on the number line, right? I'm going to visualize plugging that number in. If I plug -10 in here, what's -10 minus 3? A negative number. Negative number. What's -10 plus 1? A negative number. I don't care what the number is, it's negative. What is -10 plus 4? Still a negative number. What's a negative times a negative times a negative? Negative. So at this point, the graph would be below the x-axis because the output would be negative. I don't care how negative, it's negative. In this next interval, what's a number between -4 and -1? Great. I'm going to take that number and I'm going to plug it in. Could you pick -2? Yeah. Whatever. If I take the number -3 and I plug it in here, -3 minus 3, a negative number. -3 plus 1, a negative number. -3 plus 4, positive. What's a negative times a negative times a positive? Do you see what I'm doing here? I do the same thing for this interval, picking an easy number. What's the easiest number between a -1 and a 3? We like plugging in 0. Choose that if you can. What's the number that I picked in this interval? 10. Pick an easy number to plug in. 10s are pretty easy to plug in. You could pick 50. Sure. Pick 100. Sure. We plug all of these in, and then we read the graph. Now remember, our goal here was to find where this graph is above the axis. So our graph is going to be above the x-axis in these 2 intervals because those are the ones that had positive outputs. So to answer the question here of where the graph is above or equal to the x-axis, we would say it is above or equal from including -4 to 1 or from 3 to infinity. Those are the places I colored in on this number line, yeah? So this would be the solution. That's the interval where the solutions to this inequality exist. My question before we try another one would be, we don't have to redo all of the things. How would my interval answer change if my inequality said this instead? Just less than 0. Which intervals is it less than 0? The other one. So we would answer, we would say from -infinity to -4, bracket or parentheses? Parentheses, because it's not equal to this time. Or the interval from -1 to 3. Parentheses, because we're not including the zeros this time. creating this sign chart essentially gives you the picture of the graph. Because when we had the picture of the graph a second ago, it was really easy to see where things were above or below. This is how we see whether things are above or below. Can we do one start to finish together? Okay, I'm here with you. I'm not letting you on your own. We have example 5. First of all, what's the question it's asking here? What am I looking for in the end? The points that less than 0, so below. If we were graphing this, we would look below, but we're not graphing it. Okay, first things first, we need to solve the polynomial. So we take x plus 2 squared and x minus 5, and we set it equal to 0, which means what's the first 0? Negative 2. With what multiplicity? Great, review. And then x equal to what? 5. What multiplicity there? 1. Okay, cool. So we draw our number line. I literally don't care how far apart you put the numbers, as long as they're in number order. That's important. Do I put closed dots on these critical numbers here? No, why not? Correct. It's not equal to, so we use an open circle, meaning we're not going to include those numbers in our answer, but they are the boundaries between this graph and how this graph might change. So we set up our sign charts. Okay, what is a number in this interval right here? Sure, negative 3 would work, but let's make it aggressively negative, like way more negative than that. I like negative 10. Negative 10's easy to plug in because 10s are easy to work with. So if I were to plug in negative 10 to this factor, what is negative 10 plus 2? Negative 8. Don't care, just the negative part I care about. Great, but don't forget that one is squared. So that's a negative number squared. Yes. If I plug negative 10 into x minus 5, do you get a negative or positive number? Negative. All right. If you have a negative squared times a negative, what kind of number would you get out? A negative. Because negative times negative is positive. Positive times negative is negative. I see some question marks floating up above your heads. Do I need to say that again? Do we know how I got this minus and this minus? Yes. Okay. If I'm actually figuring out what this is, what is a negative times a negative? That's what squaring is. Positive. So a positive times a negative is negative. Okay, I heard the O's. I want you to try the other two intervals. So you're going to attempt to plug in a number in this interval and then a number in this interval. You can use whatever number you want. I recommend picking easy numbers to work with. So you do the next line. 2 lines. 2 intervals. What number did you choose to plug in the middle interval? Great choice. Plugging in 0, amazing choice. So we have 0 plus 2, that's a positive number, but we're going to square it. And 0 minus 5, that's a negative number. This is still negative. This answer could vary. What number did you plug in the last interval? 10. Thank you. I love using 10. I had classes last year just straight up not choosing 10. Amazing. How dare they? Who are they? So we should get a positive number for that one. Did we do the sign chart okay? Yeah. Great. Now let's think about the question again. I wanted to know where this polynomial was less than 0. There are 2 places where this polynomial is less than 0. That's going to be here and here. Now the question becomes, how do you write that as an answer? here's how you write it as an answer. You would say that this polynomial is less than 0 from negative infinity to negative 2, close parentheses. Pick up your pencil. Put your pencil right back down after negative 2 and go all the way to 5.
I did it right.
So we cannot include the negative 2 in our answer because it's not equal to 0. I'm not asking that question. So we have to like basically pick up our pencil, then put it right back down. So that's 2 separate intervals.
Negative 2 is not 0 itself.
Correct. Negative 2 is a 0, and we don't want things to be equal to 0 in this polynomial. We only want less than. So the question becomes, what if the question did ask less than or equal to? Okay, I'm going to write down what I'm hearing. I'm hearing you say that this should be negative infinity to negative 2 bracket, and then bracket negative 2 to 5 bracket. We could just do, instead of this, we can just do from negative infinity all the way to 5. How come I don't have to stop at negative 2? Because it's included now. This was too repetitive. We actually included negative 2 in both intervals, and that's so unnecessary. Okay, so this is how you would actually write this answer. Because it's like a combo of the two. We don't need the brackets when they're on the same number. You can just write it as 1. Are we still hanging on with me? Great. This next part's going to sound familiar. 1, because we've done this concept before, and 2, because this is actually what you did in Algebra 2 with tables. Let's determine the degree of a polynomial given tables. Before today, I had you do this using the full average rate of change formula. And for a lot of times, you're still going to need that, especially if it's asking you about the average rate of change. But if you notice that the table is changing with consecutive equal length input value intervals, meaning the x's go up by the same number the entire table, all you have to do is look at successive differences since the interval of the x's is always the same.
I learned about consecutive equal length input value.
Amazing. Yeah, say that sentence to yourself 17 times fast. You get really tongue-tied. It's kind of fun. Here's what I'm noticing. In this first table for f of x, do you see how the x's go up by 2 every time?
Yeah.
Those are consecutive in order. Equal length plus 2 input value intervals. We're good to go. All we have to do is look at the differences in these numbers instead of calculating the entire average rate of change. We can take this shortcut. Again, only because those input values are successive equal length input value intervals. How do you change from negative 2 to negative 3? How do you change from negative 3 to negative 1? How do you change from negative 1 to 4? How about from 4 to 12? Are those numbers the same? No, so this function is not linear, not degree 1. We would have known that from average rate of change. Let's check the changes in these average rates of changes. How do you go from negative 1 to 2? How do you go from 2 to 5? How do you go from 5 to 8? So this is the first degree polynomial. This is the second degree polynomial. So this degree is probably 2 because the second differences are constant. That would have been a constant change in the rate of change. Is how we would have said it a class before. That's both acceptable ways to talk about a function being quadratic or degree 2. Can we try the other table together? First things first, we check the input values. What are all the input values going up by?
3.
So I can just use the shortcut. I don't have to use actual average rate of change formula because I have consecutive equal length input value intervals. Great. So we go from negative 2 to 0. How do you do that? Plus 2. How about from 0 to 10?
Plus 3.
How about from 10 to 27?
Plus 17.
And then the last one? Ooh, 23, yes. Not degree 1. How about degree 2? Plus 8. How about this one?
Plus 7.
And then this one?
Plus 6.
Is it degree 2?
No.
Okay, we keep going. How do you go from 7 to 8? I mean, sorry, 8 to 7. And then 7 to 6? So what degree is this one probably? 3, because why? The third differences are constant. We'd call that a cubic function. Make sense?
Yes.
Okay, last concept on the back here. I know this notes were pretty long today. I'm so sorry. We got to talk about functions being even or odd, and this is very misleading because I'm not talking anymore about the degree of the function. In fact, you might want to write that up here. We are not talking about degree here. Okay, even and odd functions is a property of polynomials, a property of functions in general, and it does not have anything to, well, it has a little bit to do with the power or the degree, but not really. You have to actually know the formulas and the visuals for even and odd functions. A function is even if it is symmetric over the y-axis. So if you look at this one in the graph right here and we highlight our y-axis, do you see how I could fold this graph over the y-axis and it's symmetrical? One side fits right on top of the other.
Yeah.
That means it is an even function. Not all even degreed functions are even functions. So get those two concepts separated in your brain. An even function is not the same as an even degree. The formula we're going to use to by hand determine if a function is even is this. It says if f of negative x is equal to f of x, it is even. Meaning if you plug in a negative x and do all the algebra to reduce that function down, you should have the same function you started with. A function is odd, hold on with me, I got you. A function is odd if it is symmetric about the origin, which is nice because odd origins start with the same thing. So what we're going to do is we're going to put a pin in the origin or highlight the origin, and we're going to visualize spinning this graph around. And it's hard to do because I can't actually spin my iPad. But if we were to take this graph and like stick a pin right here and spin it, wouldn't this side land right on top of this side when you spin it? That's an odd function. It's symmetric about the origin. Okay? A little bit harder to visualize, but to put a pin in the origin and spin it. What that means analytically is that if you plug in a negative number, you will get the literal opposite function back out. Every sign changes. That's how you know analytically if a function is odd. If neither of those two things happen, it is neither even nor odd. 90%, 99% of functions are neither, because it's very specific when a function is even or odd. Let's check this. So analytically, we're determining if the following functions are even, odd, or neither. I started you off each time. I took the h function and I started to plug in negative x. We got to clean this up and see what happens. What is a negative times a negative times a negative times a negative? Positive, which means this first term is just 2x to the fourth power. Then we're going to subtract negative x squared. What is negative times negative? So this is just x squared. We compare. Once we've done all of our simplification, compare where we started with where we got. What do you notice? They're the exact same. So we write the sentence, since h of negative x is equal to h of x, this function is even. Boom. Since h of negative x, I plugged in negative x, is exactly the same as where we started, that's what that sentence says, this function is even. Can we do it again? So here's the k of x function. For the k of x function, I'm going to plug in negative x. I got you started. For the first one, negative times negative times negative is negative. So this is negative x cubed. And then 3 times negative x is negative 3x. And I have minus 1. Compare. Are they exactly the same?
No.
Are they exactly opposites? No, they are not exactly opposites. I know this sign changed. I know this sign changed. But did this one? No. So here's how we write our answer here. We would say since k of negative x does not equal to k of x, and k of negative x does not equal negative k of x, that's the opposite, then this function is neither.
Wait. So it doesn't equal. Okay, I see.
It's not the exact opposite, and it's definitely not the same. Yes?
Sure.
Sure.
Well,
Go back. Okay, sorry. So k of a negative x, meaning I plugged in negative x and I compared it to the start. It wasn't the exact same. It wasn't the exact opposite, which means it's neither even nor odd. Now what about c? If I plug in to the j of x function, if I plug in negative x, what happens to this first term? Is it positive or is it negative? Negative. So you have negative x to the fifth. What's negative 5 times negative x? Positive. Okay, we compare. Are they exact same?
no, they're opposite.
They're exact opposites, right? Every single sign changed in the function. So we say since not k, what's the name of this function? J. Since j of negative x is equal to negative j of x, the exact opposite, this function is odd. Odd, opposite, odd, origin. It's nice. Those start with O. Odd, opposite, odd, origin. Okay. Now, it gets a little bit easier when it's a visual question, right? If it's giving you a graph, we don't have to plug in negative x. We can just look. I like to do process of elimination. So does this have symmetry over the y-axis? No. Okay, so get rid of that. Does this have symmetry about the origin? Yeah, you can spin this and one side would be exactly equal to the other. So that means that this one is odd. It is symmetric about the origin. Okay? Specifically, the origin is odd. What about E? Process of elimination here. So I like to look. Is it foldable across the y-axis? No. Is it, oop, it didn't erase. Is it spinnable about the origin? No. So it is neither even nor odd. Because it is not symmetrical about the y-axis and it is not symmetrical about the origin. So visually, this is very easy to answer. You fold it or you spin it. If you can't do either of those, it's neither. I know that these notes were long today. I'm very sorry. So there's a lot of content today. 4 whole pages, but you did it. Amazing.